Last time we introduced incidence numbers associated with the CW complex, and we formulated the theorem that the matrix of incidence numbers is what makes explicit the cellular differential in the cellular chain complex. And I still owe you the proof for this statement, and to do so I already prepared, like a TV chef, the setup from last time to make sure we save some time here and then can plunge into the proof right away. So in this video, H star just denotes singular homology with coefficients in some commutative ring R, and we fix a relative CW complex X comma A. So not part of the structure, but the existence is guaranteed that we can choose push-outs, which explain how the N skeleton arises from the N-1 skeleton in the CW complex by attaching cells. So we choose such push-outs, we make such a choice, and this defines the characteristic maps of the cells. Yeah, they're indexed by I over an index set In for the N cells. And their restrictions to the boundary spheres, these are the small letter Qi N's, and these are called the attaching maps of those cells. All right, and with this choice, we could define maps Fij from the N-1 sphere to the N-1 sphere. And how did we do this? Well, we just first of all take the attaching map of the ith N cell, that's a map from Sn-1 into the N-1 skeleton. Then we collapse everything in the N-1 skeleton except the open N-1 cell indexed by J. And this quotient space is now actually homeomorphic, so I can write homeomorphic here actually, by means of the characteristic map of the N-1 cell J induced on the quotient. Yeah, if I factor out here the boundary sphere, N-2 sphere of this N-1 disk, then I obtain an induced homeomorphism here. Yeah, because this boundary sphere here ends up in this quotient space, so I've got an induced map, and that's a homeomorphism. And finally, last part of the composition, that was this homeomorphism UN-1, which identifies this quotient of the N-1 disk modulo boundary sphere with the N-1 sphere. And then I just define this arrow here as this whole decomposition, whole composition here around the diagram. Okay, so by the choice of the push-outs, I obtain these maps Fij, and these were then used to define the incidence numbers, ints ij, just by saying I look at the induced map in N-1 reduced homology. This now gives me an endomorphism of an infinite cyclic group, and therefore it is given by multiplication with some integer. And I just say this integer here is supposed to be the incidence number associated with the N cell I and the N-1 cell J. And now I can just write all these incidence matrices, incidence numbers into a matrix just by decreeing that the ijth entry of this matrix is supposed to be the ijth incidence number. And then the statement of the theorem that we want to prove today is this one. If we identify the cellular chain complex of the relative CW complex XA by means of these isomorphisms nu n that we introduced in a couple of videos ago, with a direct sum of R's down here, then actually the cellular differential, I should put this down here, so the N's cellular differential is just given by right multiplication with this incidence matrix here in this, with respect to this block decomposition. Okay, so this makes the cellular chain complex very explicit, and once we've proven this, it is clear that this can nicely be applied then to do actual computations, and compute the algebraic homology of this very explicit chain complex to come up with the original homology of the CW complex. Okay, so let's now start with the proof. So we do the only thing we know to do as algebraic topologists. We have a commutative diagram here in the category of topological spaces. So I apply a functor to this diagram, namely the functor h twiddle n-1. And if I do this, I come up with the following. So let me draw this as far down as I can. So here I've got h n-1 twiddle of s n-1. Here I've got the induced map by the N-1 by the ith attaching map. So that's the N-1 reduced homology of Qi. And yeah, to avoid confusion, I should also always put the index, the dimension of the cell as an upper index here. Yeah? So this is the attaching map of an n cell. So I write it like this. And with this, I end up in the n-1st reduced homology of the n-1 skeleton. And now I have this long arrow in the diagram up there going to the quotient space where I mod out everything but the open cell indexed by j. But I drew this arrow actually so long because I want to make an intermediate step here and say I first collapse just the n-2 skeleton. xn-1 mod xn-2. Because in the end, I want to come up with the n-1st cellular chain module on the upper right corner of our diagram, and that involves the n-2 skeleton. Yeah? It was defined as the n-1st homology of the n-1 skeleton relative to the n-2 skeleton. So at some point, this n-2 skeleton needs to show up, and it shows up here, yeah? Because I can just factor this long arrow through this earlier quotient where I mod out sort of a smaller space here, and now I mod out a bigger space, namely the n-1 skeleton, mod out everything but this j's cell. So mod out xn-1 without the open cell n-1 cell indexed by j. Right, and here I had my homeomorphism, so this gives me an isomorphism now of R modules called hn-1 twiddle of, this should now be the characteristic map of the cell j, and it's an n-1 cell, so this should be the right notation. And this now starts in the n-1st reduced homology of the n-1 disk, mod out the boundary sphere, which is an n-2 sphere. Okay, so far so good. And now I have the arrow induced by this homeomorphism un-1, so I write here h twiddle n-1 un-1. And that gives me another isomorphism now going to the n-1st reduced homology of the n-1 sphere. Okay. And okay, so maybe I'll try to move this a bit up here to make the diagram more coherent. Ah, it did work actually. So, right. Okay. And then I here got the arrow induced by Fij. So that's hn twiddle Fij. But remember, by definition, this map is just the multiplication now with the incidence number. So I can equivalently just write here multiplication with the incidence number and incident number with index ij. Okay. So this portion, this diagram commutes just by the definition of incidence numbers. And now I want to extend this diagram as to rediscover our original diagram of which we asserted commutativity. And to do so, well, what I can do here is I can use the suspension isomorphism, and I actually use it n-1 times until I end up at the 0th reduced homology now of the 0 sphere. Suspension, let me just write to the n-1, even though each suspension isomorphism I apply here is actually a different one. Yeah, I always have to lower the degree by 1, but I think the notation is suggestive. And I can do exactly the same thing here. So this is suspension n-1 times. These are all isomorphisms. And I end up at the 0th reduced homology of the 0 sphere here. And now if I consider this composition here, then this is actually, again, just multiplication with the incidence number. Yeah, because I'm using one and the same isomorphism here and here. So commutativity in this diagram is just by the homomorphism property of this isomorphism. Yeah, so that definitely commutes. And finally, we discussed a fixed identification now of the reduced zeros homology of the 0 sphere with the coefficient ring. And it's not so important which identification we actually use. It's only important that we use the same now on both sides. And I think we made an agreement how we did it. We said, okay, this reduced homology is the same as the non-reduced homology relative to -1, to the point -1 in the sphere. And then I excise this point -1 and I end up at the point 1 here, sort of. And this is the one I use. This is all isomorphisms. I take the same isomorphism here. And now, since the given homology theory we said in the beginning is just singular homology with coefficients in R, there we already proved that the homology of a point is the ring R. And again, since we're using the same isomorphism on both sides, the composition here is just, this composition is just the multiplication again with the incidence number.
So the isomorphism between H0 of the point and H0 reduced of S0 is, what's the map?
So,
given by inclusion of the point to 1, or is it another map?
So what I wanted to say is I first take the isomorphism from reduced homology of S0 to unreduced homology of S0 relative to a point.
Mm-hmm.
And then I excise, and excision is it's an inclusion in this direction, right? It's, yeah.
Right.
It's the inclusion of point, comma, empty set to point, comma, point.
Probably the same as saying that you include this point to the point 1?
Maybe.
Maybe.
Yeah. But again, it doesn't really matter what identification we use here, so long as we take the same on both sides.
Do it consistently on both sides.
Yes.
Yeah.
And so long as we use the same isomorphism when defining our isomorphism nu in the beginning of our commutative diagram. Yeah. So let's just say once and for all we use the same thing in all these, in all these steps. Okay. So the lower portion of this diagram now looks already as what we are trying to achieve here. So let's now try to find our way through the jungle and come up here with the cellular chain modules. And to do so, we extend this diagram here now on top. And, well, I want to come up here with the nth non-reduced homology of the n skeleton relative to the n-1 skeleton. And I can do this in a two-step procedure. I first take the differential in our long exact CNDR sequence that we derived in a couple of videos ago. So this comes from the nth reduced homology of xn, mod out xn minus 1. And to be pedantic here, when we derive this long exact sequence, and also the boundary operator of this long exact sequence of a CNDR, we require that that CNDR be non-empty. Yeah? So let's now assume our CW complex X is non-empty, so that these are actually non-empty CNDRs. And we can assume that because if X happens to be empty, then the statement of the theorem is trivial. Yeah? Then you've got just the zero diagram, which definitely commutes. So we can assume that. Okay, and now, oops, I'm already running out of space, but I think I can manage with what I got here. Let's put this a little lower. Okay, because I just need one more arrow on top here. Namely, I now can use our isomorphism from the collapse proposition. Well, give me my pen. There we go. So we had this, for a CNDR, we had this proposition that the relative homology of this CNDR is isomorphic to the reduced homology of the quotient here. Yeah? So this is the arrow we use here. And actually now we are happy because this is by definition the nth cellular chain module. And here we are already one step closer to our goal. Here we want to come up with the n-1st cellular chain module, and that's by definition the n-1st homology of the n-1 skeleton relative to the n-2 skeleton. And I get that object right away when I here use again our collapse proposition. So here I've got this collapse map going to the non-reduced homology of the n-1 skeleton relative to the n-2 skeleton. Okay, and now from here to here, I of course want to set in or apply my boundary map in the cellular chain complex. but let's just remember how this was defined. This was the boundary map in the triple sequence, yeah, of the triple n skeleton, n-1 skeleton, n-2 skeleton. And the boundary map in the triple sequence, again, was defined in a two-step procedure, as you will recall, by first using the ordinary boundary map of our homology theory, in this case singular homology, which goes to Hn(xn-1). And then we simply have an inclusion here of the pair n-1 skeleton, comma, empty set into this pair here and the induced map in homology. That's the second one. Yeah? So this composition here is actually the nth cellular boundary map of the cellular chain complex. Okay, so far so good. And now let me extend this diagram, it's still not done. Tiny little on the left. Namely here, I've got as a space the n skeleton mod out the n-1 skeleton. So what this space is here, it's just a one-point union, a wedge sum of as many n spheres as I've got n cells in my CW complex. And now I pick out one of them, sort of, yeah, by using the characteristic map of the ith n cell. So this was the map Q, I, N. And this induces, again, a map of quotient spaces because the boundary n-1 sphere is mapped by the attaching map into the n-1 skeleton that's mod out here. So from this map, I obtain an induced morphism here from the nth reduced homology of now the n-disk mod Sn-1 here. Yeah? Okay, so now let's connect this portion here of the diagram, the nth reduced homology of the n-disk mod out the n-1 sphere, with this part here of the diagram. And we do so by, first of all, again, applying our homeomorphism, un. So we use the induced map in nth reduced homology. And this is now, well, it's an isomorphism because it's coming from a homeomorphism. And this is now going to the to the n sphere. Yeah, that's the homeomorphism that un provided. And now from here to here, I've got again our suspension isomorphism. Yeah, the nth homology of the n sphere is isomorphic to the n-1st homology of the n-1 sphere. So this is just suspension. Okay. So this is our lovely diagram. And now two things remain to be seen. First of all, why does it commute everywhere? And secondly, why does it prove what we want to prove? Yeah? So let's first maybe treat the commutativity. So this part of the diagram actually commutes, as one can see by putting in here some auxiliary map. So here I've got the arrow D, which is just, again, the boundary map in the long exact sequence of the CNDR dn, Sn-1. Yeah? So this is the boundary homomorphism of this one. And then I see that this part here commutes just because this is actually how the suspension isomorphism was defined. Yeah? So it commutes by definition of the suspension isomorphism. Suspension meant identify the n sphere with the quotient of the n disk mod the n-1 sphere, and afterwards apply the boundary map in the long exact CNDR sequence. Yeah, this is exactly what this is. So this triangle commutes. And this triangle here also commutes, and this is just the naturality statement of the long exact CNDR sequence. Yeah? So I've got my long exact sequence of the CNDR n-1 skeleton included in the n skeleton, and I've got my long exact sequence associated with the inclusion of the n-1 sphere in the n disk. And I have a map of spaces between these pairs, and this induces a map of long exact sequences. And this commutativity is just the commutativity of the boundary morphism part of this map of long exact sequences. So that also commutes. Okay, so maybe to make things better visible, let us just use the undo function to remove the green part. So we now convinced ourselves that this commutes. Okay, and we go on to the other squares. So let's see. So this big rectangular square here commutes as we argued in the beginning because it had an underlying commutative square or rectangle of spaces. These two commute as we already said. So the only thing that still needs proof is that this 6-term mesh here in the diagram actually also commutes. And to do this, to show this commutativity, let me again, well, maybe to make it, maybe it's going to be too cramped if I just put it inside there. So maybe let me write a new diagram down here to prove that commutativity. So let's just copy what we had there. We had the nth homology of the n skeleton relative to the n-1 skeleton. Then here we had the boundary map going to the n-1st homology of the n-1 skeleton. And here, let me put this more or less in the middle, okay. Here we've got the inclusion to n-1, xn-1, comma, xn-2. Here we had the collapse map, so it was this isomorphism going to reduced homology, xn mod xn-1. And from here we went down to, by the boundary map, to the reduced n-1st homology of xn-1. And what did we have here? Here we have the collapse map again. So this is the isomorphism going to the n-1st reduced homology of n-1 skeleton mod out n-2 skeleton. Right. And here we've got the map induced from the quotient map on the level of spaces. Okay. So we have to verify that this diagram now commutes to end up our proof of commutativity of the big diagram. And we do this by, again, adding an auxiliary object here in the middle. So this is why I wanted more space. And what I do is I take a point in the 0 skeleton, say. So again, I'm using that the CW complex is non-empty, as I already discussed that I may assume this. And then I write here the n-1st homology of the n-1 skeleton relative to this new point x0 here. And now I connect this object with as many objects here as I possibly can. And well, first of all, I have this map here. This is just, again, this collapse map. Yeah, if I mod out a point from a space, then I get the same space, but this makes me end up here in reduced homology. So this is, again, our collapse proposition, which I use here. And then I've got a map in from here to here, which is just the boundary homomorphism in the triple sequence, yeah, of n skeleton, n-1 skeleton, and this new base point here. And I also got a map here, which is just the inclusion of the pair xn-1 comma empty set to xn-1 comma this point here. And I finally also got a morphism in this direction, again coming from a map of pairs or spaces, because I chose x0 in the 0 skeleton, so it lies in particular in the n-2 skeleton, and I have this induced map here. All right. And now we look at the various squares and triangles we see here. So first of all, this one does commute actually just by definition of our boundary homomorphism in the long exact collapse sequence. Yeah? So if you go back to the proof of the long exact collapse sequence, it was just that we used the triple sequence with an additional base point. That's where the assumption on empty went in. And then just we identified now this boundary homomorphism with the boundary homomorphism in the triple sequence under these collapse isomorphisms here. Yeah? So this is just the definition, commutes by definition of the boundary map in the long exact collapse sequence. Then why does this triangle here commute? This is just the definition of the boundary map in the triple sequence. Yeah? So the boundary map in the triple sequence was defined as taking the ordinary boundary map and then include back into the pair here. Yeah? So this does also commute just by definition of the triple sequence boundary map. And the remaining two parts here, they actually do commute because they come from an underlying commutative diagram of spaces. Yeah? So this is just applying the n-first homology to this diagram of pairs of spaces, and the same thing down here. Yeah, so I mean, here I've got my collapse map, here I've got my collapse map, but these collapse maps actually, if you look back there, came from maps of spaces, and they just commute with these maps of spaces. So it's just applying a functor to a commutative diagram that yields a commutative square here. Okay. So all these little things commute, so we should also make sure that then the outer big thing commutes. So let me just show it to the camera. Yeah, so commutativity is claiming that going along here is the same thing as going along here. Why is this the same thing? Well, going along here, whoops, is by commutativity here the same thing as going along here. Now by commutativity here, that's the same thing as going along here, and by commutativity in this triangle, that's the same as going along here, and finally by commutativity in the last triangle, that's the same as going along here. So actually these small commutativities gave you the commutativity of the outer part of the diagram, and that's actually all we needed to show. Yeah. So now we know that also this one commutes, and well, it's a quick check that now actually the whole diagram also commutes, as we have seen that all these meshes commute. Okay, so this is a huge commutative diagram of R modules, and now why does it prove our assertion? That's because of the following. Consider this composition here in the diagram, and I just say this composition is actually the inclusion of the ith direct summand in the direct sum decomposition of the cellular ends of the nth cellular chain module. Yeah, because I mean this was this bunch of n spheres glued together at one point, and this characteristic map singles out now the n cell indexed by I. This is just the R summand. So I mean, following this isomorphism down here, suspension isomorphism until down here R, then actually this map here, up here, is just the inclusion of this R summand corresponding to the ith cell. And similarly, on the other side of the diagram, I have here my n-first cellular chain module. And if I consider this composition here, going along here, going along here, going along here by the inverse of this arrow, then I end up again at this group Hn-1, Dn-1, Sn-2, which by suspension isomorphisms is just this R term here, and this composition that I just showed to you, going here, going here, going here. This is now just the projection onto the jth summand in my direct sum decomposition of the n-first cellular chain module. And now what the diagram says is, maybe I should use the modern technique here and make it available at one side. Should have done this earlier. So, like this. Okay, I think now it should be visible. So now if I follow this arrow, so here I've got the inclusion of the ith direct summand, and if I then apply the cellular boundary homomorphism, which is this composition here, and then I project onto the jth summand, again in the direct sum decomposition of the n-first cellular chain module, then under these suspension isomorphisms here and here, this is the same thing as multiplying with the ijth incidence number. Yeah? And that is precisely the statement of commutativity we want. Yeah? If by first injecting the ith summand, then projecting to the jth summand, we get this ijth incidence number. That means that as a whole on the direct sum decomposition, this map is given by matrix multiplication with this incidence matrix.